Hello, my name is Samuel Rurangamirwa. In this video, I'm presenting my final machine learning project titled Predicting Cryptocurrency Pricing Direction Using Machine Learning and Deep Learning. This project was processed on my local PC using a local Python and Jupyter Notebook environment. The objective to build a complete machine learning pipeline that predicts whether the BTC or USDT price will move up or down in the next candle using historical cryptocurrency market data. The problem is a binary classification problem. The target is 1 when the next closing price is higher than current closing price, and 0 when the next closing price is lower than or equal to the current closing price. I chose this topic because it is connected to a financial cryptocurrency market analysis. Many traders use technical indicators such as RSI, MACD, moving average volume volatility, and Bollinger Bands. However, using indicators manually does not prove that they are predictive. This project tests whether these markets features can provide useful information when used with traditional market learning and deep learning models. The dataset used in this project is BTC USDT historical OHLCV data. OHLCV means open, high, low, close, and volume. The dataset is external market data and not a built-in dataset from Scikit-learn or Keras. This is important because the project requires an original or open source dataset outside those libraries. At the beginning of the notebook, I imported required libraries. These include pandas. So if you go here in inside dependence, so you will see some libraries that I installed. So in these libraries includes pandas, NumPy for data processing, Metasploit for visualization, Scikit-learn for traditional machine learning models and evaluation matrices, and TensorFlow for modern learning processes, as it is shown on this part right here. The next step is data loading. Book loads BTC USD market data, standardize the column required for pipeline. So, all right, let me go down right here, dataset from Binance. Okay, these ones. So most important columns are open time, open, high, low, close, and volume. When additional Binance styles columns are available, such quota asset volume, number of trades, take a buyer base volume, and take a buyer quota volume, the node also uses them. After loading the data, inspects the dataset. I check the number of rows and columns data range missing and duplicate timeline. This step is necessary because financial time series data must be clean and correctly ordered. If timestamps are duplicated or missing, model evaluation may become unreliable. The next major step is future engineering, creating several groups of futures. First, create return-based futures such as percentage return and log futures. Second, create candle structure futures such as high, low range percentage, open close change percentage, upper week percentage, and lower week percentage. These futures describes how price moves inside each candles. Also create a volume including change, quarter volume, take-a-buy ratio, trade changes. These futures helps represent market activities, buying pressure. For trend information, I calculated simple moving average for 5, 10, 20, 30, 50, and 100 period. Also calculated the distance between price and each moving average. For experimental move average, I use EMA 12 and EMA 26. For volatility, I calculated rolling volatility over 6, 12, 28, and 48 period. Also calculated rolling mean return momentum indicators, calculated LSI with for 14 period setting and marked using first period 12, swell period 26, and signal period 9. Finally, I created Bollinger Band feature including upper band, lower band, bandwidth, and the price position inside the band. The target variable was created using the name candle cross price. If the next cross was higher than the current cross, the target become 1. Otherwise, it becomes 0. The design prevents future information from being used as an input feature. Future price is used only to create labels. After future engineering, I check the target distribution. This is important because if the class are imbalanced, accuracy alone can be mislead for reasons. Evaluate models using accuracy, precision, recall, F1 score, and raw record AUC instead of relying on the accuracy. So without furthermore, let's pass through the notebook. So in notebook, we can see we have a downloadable dataset from Binance, of course. Here, we make sure that we are not using Scikit-learn, as you can see on the dataset. So this was the one and the result. Okay, downloaded all the dataset we needed for BTC USDT 1 hour row, as you can see right here. And then we go to the data inspection. Of course, here we have to inspect the open, high, row, cross, volume, number, trade, as you can see right here. And then we see exactly the chart of how the market was when we see the BTC USDT cross price and the BTC USDT volume, how it was operating. Then the future engineering here, you can see the model should only use a raw price. We added a technical and statistic features, the candle structure, momentum, trend, volatility, volume, behavior, target. And this creates, I created here these functions that will help us to deal with the RSI, MACD, as you can see, engineering features, as you can see right here. And then we got this part, can see right here, that will evaluate each part. So the target distribution on this part is which. This checks whether the dataset is balanced. If the target is heavily imbalanced, accuracy becomes mislead, and F1 rock AUC should receive more attention. So on this part, you can see here the way things are. You can see exactly how the target distribution will be operating. And then here we have the time-based training validation test split, which will use 70% training, 15% validation. And here there's no random shuffle is used because this is time series, of course. So here we will do drop column, open time, cross time, future cross, future return, target. And here we do things here that we evaluate each part, and then we get the result for our train, validation, and the test. So, and on this part we get also our data split, which is train, validation, and test. Evaluation helper function here, these functions, we keep the notebook module and reduce repeated codes, of course, because here we will be evaluating prediction, experiment ID, model accuracy, precision, recall, F1, recall, AUSC, and notes. And on this part, we also print the matrices. We will also do a plot, of course, and we will have the plot rock curve and the base model here, the model that must be a simple baseline to be used. Baseline predict the most majority classes from the training set, and it will give us exactly all the listed thing we had here on matrices. Of course, this will be the final results. And the traditional machine learning experiment, where we have to do experiment 1, 2, 3, and 4, where we do logistic regression, SVM with RBF kernel, random forest, gradient boosting. And on these models, we have to train everything that we have. And training experiment 1, logistic regression, so we will have these results, of course, and we will have also these charts that will show actual logistic regression confusion matrices, and another one which will show a rock curve. And we go to the experiment 2, which will give us SVM, RBF, of course, to show confusion matrices and also show the rock curve. You can see that the thing here has also the operation are really working accurately and the data are different. And if we go to the random forest 2, which is experiment 3, we see the confusion matrices, and also we see the ROC curve of this random forest. And experiment 4, which is the gradient boosting. In the gradient boosting, we also see if it's we will see this chart of it, and also we will see this ROC curve we can see right here, which is for positive rate and the positive rates right here. So the future importance of tree-based model. Future importance helps explain what the model is using. This used for report discussion, but do not overtrust it. Financial futures can be unstable across the market regimes, especially when you are dealing with the stock markets. Most of the time, market changes randomly based on the decision of someone high, those kind of things. It's the thing that most of the people need to consider when they are checking about these things. So this is the random forest future importance. So, and everything here as aligned, this SMA 5, this SMA, all of the things here, as you can see, it's really tested very well. And here we go to the prepare scale data for TensorFlow. Of course, here we need to do a neural network. Usual need scale input features. The scaler is fitted only on the training set to avoid data leakage. So this is the thing that we did right here. TensorFlow also data pipeline. So here what we are doing is the assignment asks us to TF data. We create the efficiency batch data for training and evaluation. Of course, here we have to create them. And after creating them right here, you can see we keep them in a training DS, validate DS, and this DS. Don't mind about this error. It's just one of the COD failed unknown. It doesn't affect my code in any way. So TensorFlow sequential API. Here I go to create this API ones that I will be needing, which will have the rare input, the dense, the batch, normalize, the dropouts, dense, batch normalize, dropouts, things like that. And we do the model compile that will optimize our carriers, optimize the Adam, because here I'll be using Adam, and those will be binary cross trophy, binary cross entropy and accuracy things, this in matrices. And here we have early stop and sequential model, and here we say sequential model summary and historic sequence. So here we have sequential model. Here, as you can see, all things listed. We will see the total params, the trainable params, and trainable params, as you can see right here. So all of these things operates exactly the way I hope that it would operate. And I have here a sequential model ROS curve. Of course, it will show me the ROS curve, and here I have the sequential model AUSC curve. And then here I will see the sequential model predicts and the sequential matrices, of course, here. And this will be the sequential model confusion matrices, and here we have the model ROC curve. So the TensorFlow function API. So here the experiences function API neural network with the residential star skip connection. The function API is useful when model topology is more flexible than the simple tracks. So in this function, this is where I build my functional model that will give me the functional crypto direction model, as you can see right here in this table, how everything is categorized, the layer, the output, the param, and the connected to. And I will have my epoch here running for the test, and the plot learning curve. Of course, here functional model, everything will be operating here. The functional model ROS curve will be this one, and I will have the functional model AUSC curve. So this will be the epoch, and here we will be having the ROS, the AUSC and the epoch. So this will be the functional model confusion matrices and the function model ROC curve in this part. So going to the sequential based deep learning model, and this one, which is on experiment 7, the sequential model using the recent historical windows. So this model uses the last look back candle to predict the next candle direction in this more natural for time series data than using raw at a time. So here we have our results, of course, from our function we have here, which is making the sequence, and we have the build LSTM model, of course, here, and the result we have everything running. The model LSTM crypto direction model will be created, and we run the epoch to make sure that everything is accuracy, by checking the accuracy, the AUC, the loss, the precision, everything running correctly. And then here we do the prot for LSTM models to check how the things are being trained, and LSTM model US curve also, which is operating well. And here we will have our model confusion matrices and ROC curve as is shown. So for our experiment result tables, the report should not be listed in numbers, so it should be explaining the result changes. So use this table to write the report. So this is the table I used to write the report, interpret for running the notebook. And here there's error analysis. So here they are also false positive mostly happen during the high volatility. Another one is false negative mostly happen after sudden reversal candles. So does the model fail? So these are the error reports that I should be explaining based on my deeds app right here. And I have also prediction set, which I'll be seeing the sequential function and RSTM, all right. And I have here the chosen model for error analysis, which is sequential, and error correct. On this part, I will be seeing the error type, the correct, the false positive, the false negative, name count, data type, and integer 64. So on this part here, I will be looking upon the column, which will show RSI 14, MACD history, volatility 24, historical range, and our BBD width, and this will be the actual error type, how things will be, and MACD historic, and also volatility will be seen like this, and also this error type for high range, and also BBD width by errors. So this is all. This is how I saved, of course, my model and artifacts, which will be found on this artifact part right here. Everything's really saved as it should be, and also the data that I need, which is saved on this part of CSV. Thank you for following the presentation. So I think that was all for this project. Yes, thank you. Ciao, ciao.